Okay, so welcome back everybody. From today, we will be talking about power series, which is the theme we have for 11.8, 11.9, and 11.10. Okay, so let's talk about power series first. So let's think about it. We have 1 plus 1/2 plus 1/2 squared, which is geometric series, 1/2 cube. Okay, dot, 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 dot. With r equals 1/2 less than 1, so we know it's convergent. Moreover, we know the answer is going to be 1 over 1 minus 1/2, which come from the formula a1, which is 1 divided by 1 minus r. In this case, it's 1/2. Similarly, we can do this. 1/3 plus 1/3 squared, dot, dot, dot. R equals 1/3. The sum is going to be 1 over 1 minus 1/3. From here, we can see the pattern, right? Let's try some more numbers. 1 plus 4 over 5 plus 4 over 5. I can even put a negative here. Dot, 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 dot. It's going to be 1 over 1 minus 1, that's 4 over 5. Finally, 1 plus 3/2 plus 3/2 square plus 3/2 cube. Dot, 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 dot. Equals 1 minus 3/2. Well, notice on the left, every single term is positive, but on the right, what you have is 1 over 1 minus 3/2, which is 1/2, negative. This gives you a negative 2, which gives you a negative number. This is very counterintuitive until you realize, okay, r equals 3/2. This is divergent, and because it's divergent, you actually cannot write down anything up to here. Okay, that's some simple fact we get from geometric series. But now what I want to do is I want to write all these kind of patterns into a general pattern. That means I want to write it in all kinds of r. Then what we can do is we can actually take 1/2, 1/3 to be a general r. And then we say, hey, it's nothing but 1 over 1 minus r because your 1 is just your a1. Okay, and this is only convergent if r is less than 1 in terms of absolute value. So far, so good. And then what I want to do is I want to rewrite the thing to put this one to the left. And then whenever I see r, I can certainly change it to be another letter, x. I put this one on the right. And this is convergent if x is less than 1 in terms of the absolute value. And then the whole thing I claim becomes super interesting. And let's take a look. Number 1, we have a function. Number 2, we rewrite the function to be the same as the sum of a lot of terms, and each term is nothing but a power of x. So an infinite sum of power functions. Then we give this one a name that is called power to state power function, series to indicate we want to do the infinite sum. So this is the definition of a power series. You have a sum of a lot of powers of x. Okay. And this sum goes forever to infinity. Why is it interesting? Well, if you don't look at the infinite term, you just look at finite term with 2 terms, 3 terms, 4 terms, and keep going, you realize this is nothing but a linear function, a quadratic function, a cubic function. And the more terms you take, the more terms you have. But nonetheless, there will be nothing but a polynomial. So from here you can see, basically you take a function and rewrite it to be a polynomial. But this polynomial is kind of special because it never ends. So it's a polynomial of infinite order. But nonetheless, it's very similar to a polynomial for a lot of properties. Okay. Now what's going on here? Basically, you take a function and you rewrite it to be the sum, actually an infinite sum of a lot of easy functions, which is power. Power function is probably the easiest function you can think of. Then you have a lot of interesting properties. Number 1, what's the derivative of this? Well, you say, well, I apply quotient rule, I need to know the derivative of 1 over x and chain rule and whatever. But now you don't have to. This is equal to this, right? dot, 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 dot. Then the derivative of this one is going to equal to the derivative of this one. That is nothing but 0 plus 1 plus 2x plus 3x squared plus 4x cubed and dot, 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 dot. This will be the power series of the derivative of this function here, even though you don't know what the function is. And we claim this, in some case, is good enough. Another thing you can think about is actually the integral of this, which again may be difficult, but the integral of this, which is the power series of the same function, which represent the same thing, is nothing but the integral of polynomials. Square, okay, 1/4 to the x source. This comes from this. Okay, and keep going. Make sense so far? So basically, you have a function, but once you write the function to be a power series, which is very similar to a polynomial, the derivative of the function become a derivative of a polynomial. The integral of a function become an integral of a polynomial, but the integral of a polynomial is super easy. The derivative of a polynomial is also super easy. Moreover, the root of a polynomial is easy. The graph of polynomial is easy. So everything you want to study for this function, you can go ahead and study a power series instead. And this power series will give you a very nice property because it's basically a polynomial. Okay, of course it goes forever. That is very powerful. That means any random function you write down, for example, some function really difficult. Let's say we want to see the derivative, integral of this thing. Okay, it's very difficult, right? But if you can write this thing to be a power series, I just made something up. Okay, it's going to be harder than this, but if you write it to be a power series, 1/3 x squared minus, I don't know, 1/22 x to the cube and dot, dot, dot. And then to do the integral of this one instead, every single term becomes super easy because it's nothing but a power. Power is very easy, no matter what kind of operation you want. So basically, to study any function, you can turn it to be the study of just power function. And we know everything about a power function. Derivatives, roots, everything is just easy. Okay, that's beautiful. Now you may say, well, this is a trade-off. We have something hard. We turn it into something easy. Of course, there's no free lunch. So we actually turn it to be infinite. Many easy ones. Okay, but then what you can do is you can actually take this one. I write it to be this. And then you say, well, infinite is actually really difficult, but there's nothing to stop you to just take the first 3 terms. And then you just say, this is not exactly the same, but this is just an approximation. And as long as it can show the arrow is under control, then to use this function to replace this one will not give you too much of arrow. Then you can actually study this one instead. But this one is way easier than what you have from here. So everything we learned before in series, when they actually take only finite terms, we say this is our approximation. As long as the error is under control, then every hard problem become a multiple easier problems. And then you can actually feed all these things as long as it's finite to a computer, and the computer can actually do the stuff for you. To see an example, let's take an example from Desmos. So number 1, I want to show you the graph of the thing we just talked about, which is 1/1 minus x. Okay, the red one is the graph. Now let's see the power series. Of course, we cannot type in infinite many powers. We just do several. The first one is 1. Okay, the blue line. Clearly, it's not great. But now let's add one more. Let's add x. Okay, and then let's add x squared. Let's do more terms. X cubed, x to the 4th. And what do you see? Well, what you see is this red line is replaced by the blue line here. So that means if you want to study everything about the red line, you can very well just study the property of the blue line. Okay, But the blue line will be super easy because it's just a power, it's a polynomial. That is very great. Now, of course, another thing you can see is this one doesn't work for anywhere when you try to replace the red line to be a blue line. It only works here. Okay. Then, if you go back and recall what we did there, we try to prove that this special power series only works when the series is convergent. That means it only works when your x is less or equal than 1, which means it will work for any number between -1 here and the +1 here. From here, you can see the graph still doesn't work that way. Okay, it only works roughly from -0.5 to +0.5. But in order for that thing to work for every number between -1 and 1, theoretically, you need to add more terms. We only need 4, but you can easily do 6. Now you can see it's actually more general. So if you keep adding more and more and more terms, eventually you will be able to see, okay, the blue line basically overlap with the red line if you do infinitely many terms for all the numbers between -1 and 1. Okay, so that is what we're trying to do. We take a function, we take any function, we rewrite it to be a power series. Once we rewrite it to be a power series, then it's almost like a polynomial. Then everything we would like to do this with this, we can basically do it with this one, like taking the derivative, taking the integral. But this one will be so much easier. We're trying to do here. Okay, plus you will be able to use a computer to even do approximations, because if you have infinite many series, a natural question to ask is, if I take 1 million terms, would that be enough to control my error to be under a certain kind of precision? Okay, so that's what we're trying to do. In order to do that, there are several important questions. Number 1, we want to define what is power series. Number 2, given a random function, we want to know how to write it to be a power series. Number 3, even though we write it to be a power series, we want to know when can we do it, and when can we not do it, or we just simply want to know when does it converge. Because if it converges, we can do it. If it doesn't converge, we cannot do it. If you recall the graph, you can easily see the graph doesn't work everywhere, and it only works for a number between -1 and 1. So our job is, once we have a function, once we have a clever way to find the power series, we need to have a way to test for what kind of numbers this power series will work, and for what kind of numbers this power series will diverge. Okay. For this class, this section, we focus on the definition of power series. We focus on how to define if it's divergent or convergent. For 11.9 and 10, we actually start with a random function. We see how to write them into a power series. Okay, so today, let's just nail down the solid foundation. Okay, so what's the definition of a power series? I want you to think about a power series centered at A. The formula is given by this. Okay, each Cn is called a coefficient. A is called the center, and we start from n equal to 0 to include the constant term. So let me try to write down what I mean by that. Okay, number 1, several examples of power series. The first one will be the one we had in the example. Sum n from 0 to infinity, x to the n. If you write it out, it's nothing but 1 plus x squared plus x cubed plus x to the 4th, dot, 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 all the way up. Okay, to see this is a power series, we need to find several things. Number 1, remember a general power series look like this. For this case, let's focus on this part first. X minus a to the n. For our case, we have x to the n. Okay. That means a equals 0. So this is the power series centered at 0. Okay, that's our first observation. Okay. Second thing I want you to focus on is this Cn here. that will be the coefficient before each term. As far as we can observe, the coefficient before each term, in this case, are 1. So what we can write down is, yes, we do have Cn, and Cn equals 1 for n equals 0, 1, 2, 3, dot, 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 dot. Note, this is a little bit different from the series we had before. Our original series started from 1. This one started from 0. And if you wonder what happens, you just plug in 0. You have the first term is going to be C0. X minus a to the 0 power. And as far as we know, anything to a 0 power is 1. So it's just C0. So this one is actually especially designed for the constant term. So if you think about power, we think this is the first power, second power, third power. But actually, we do have a constant in the front. We will think about this one as the power 0, which means x to the 0, which gives you a constant. So that's why we start from 0. Okay, so this is a nice power series. Let's talk about another power series. Let's talk about 1, x minus 1. Oh, no. Let's do 1 plus x minus 1 divided by 2 plus x minus 1 squared divided by 3 plus x minus 1 cube divided by 4 and dot, 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 dot. Okay. Now let's observe what we have here. Number 1, is it a power series? Well, do you see power? Yes, I do. I see the power of x minus 1. Okay, 1 power, second power, third power, fourth power, and keep going. So this is what we have. That's the power part. Then in this case, our a equals 1. The center is x equal to 1. Okay. Now second, what do you observe for the coefficients? Coefficients are 1, 1/2, 1/3, 1/4, and keep going. Clearly, we have a formula for this. That is 1 over n. But now notice, be careful. The first term is going to be when n equals 1. And the very first term is a constant term, which is 1. It's actually corresponding to n equals 0. So you want to modify that thing a little bit. You want to change it to be, let me see. One over n plus 1. This will implies when n equals 0, you have 1. When n equals 1, you have 1/2. And n equals 2, you have 1/3. Because technically, we start from the 0 term. Okay? So then we write it down all together. This is going to be the sum x minus 1 to the n over n plus 1. If you're not familiar with this, try to write down several terms starting from this formula and try to see we did reproduce whatever we have here. Okay, so you will be able to recognize a power series from this format or from this format. Okay, and if you get confused, I think the best way to do is actually just write down several terms until you see the power. Okay, so let me say it again. This is the power 0, power 1, power 2. You recognize it's a power because you realize it's the same term, but raised by a power constantly. Okay, and then you try to match the coefficients, and then you can actually write down the formula for this. Let's try a third one. Sum n from 0, infinity, x to the 2n. Okay, this is very easy to do. If you write it down, it's nothing but x to the 0, which is 1, okay, plus x to the, when n equals 1 is x squared, plus x to the 4, plus x to the 6. Okay, then the question becomes, is this one a power series? Clearly, this is a power series with even power only. There's no x cubed. There's no x to the 5th. All of them are missing. Do we have to include all the possible powers? Well, I would suggest you to think about things in this way. We always include all the powers, but If we don't have some of them, we simply just put a 0 at the beginning. So instead of saying we're missing some of the terms, we say we do have all the terms, but some of the coefficients are going to be 1 if n is even, but some of the coefficients are simply 0 if n is odd. Okay, so 2 points what I'm trying to make here. Number one, we do include all the powers, but some of the coefficient can be 0. Therefore, sometimes you may not see actually the power because you have a 0 coefficient. Second, what is C2 here? Okay. If you just go back to the original definition, maybe you think C2 is 1 because C2 is the second term. Let me take it back, C1. Okay, you may think this is C1 because C1 is simply the one after C0, which is the second term. But I want to make it firm that in this case, your C1 is going to be 0. So C1 or Cn is the coefficient of the nth power. So don't see like C3, that's the fourth term. No, C3 is the coefficient corresponding to x to the cube. And if you don't have x to the cube there, that is simply 0. Okay, so for this case, you do have a C3, which is the one corresponding with x to the cube. In this case, C3 is 0. Instead of saying C3 is actually the fourth term, which is 1. That is not what you're going to do, because then your C3 will be paired with x to the 6. That will be a confusion of index. Okay, so that's the definition of a power series. Very easy to understand, but it takes some time to get used to. You have two ways of seeing it. The first one is you write everything out. You do see it's nothing but just power. Okay, then clearly it's a power series. Or you may recognize this format. The format I just wrote down, actually by definition. This format here. Okay, that will require you to recognize, okay, I do have a power part, which is the to the n part, and then I do have a coefficient. And it better start from 0. Okay. Okay. Now we want to go to the second thing. Let's assume I give you a power series. How do you know if it's convergent or if it's divergent? Let's take a look. Number 2. Okay. Let's take an example like this. Let's take sum n from 0 to infinity, n 3 to the n, x to the n. Okay. Let's think about convergent or divergent. Okay. Well, how do we think about this thing? Number 1, is this a power series? Well, let's try to see. If you take this one, you write it in this way. I clearly see a power series. This is the power part. These will be all my Cn. If you have to write it down, it's going to be 0 plus 1 over 3 x plus x squared 2 over 3 squared, which is 2 over 9. So you do see there are coefficients, right? And there are powers. So this is clearly a power series, one way or the other. Now, how do you show this one is convergent or divergent? Well, we have so many series tests. We have the integral test. Okay. We have the comparison test. We have the alternating series test. We have the absolute convergence test. We have the ratio test. We have the root test. Plus, before everything, we have a test of divergence. So we have all these kind of things, right? But remember, if this one is convergent or divergent, it really depends on x. Then you have to go back to all these things you have and think about which one is more convenient to solve for multiple x. Okay, the right logic is if I tell you x equal to 1/3, try to see if it's convergent or divergent. If I tell you x equal to 1/4, try to see if it's divergent or convergent. But what we want to do is we want to do things reversely. We want to say if it's convergent, what should my x be? You should pause and think about it and try several ones, and then realize eventually ratio test is your only option. And let me show you how. Okay. The ratio test. You always do the ratio test. Okay. You can try the others by yourself. I will try to save some time here. But let's see. This is an plus 1. N plus 1, 3n plus 1, x to the n plus 1. All right. Now, an plus 1 over an. That's what we do with ratio test. We let n goes to infinity. This is going to be limit. N goes to infinity. N plus 1, 3n plus 1, x to the n plus 1. Okay. Divided by 3 to the n. N. Your x is going to be divided, so x to the n is here. Remember, you can pause any time to verify what you have. So try to make sure that you understand why x to the n is on the bottom. Okay. Then what we can do is we can start to cancel. We have a 3 left. So what we have here is limit n goes to infinity. Absolute value. Let's decompose them into 3 parts. Actually 2 parts. N plus 1 over n with a 3. Okay. Times x, because x to the n plus 1 and x to the n, they cancel. You just have one more x left. Okay. Now ask yourself, what is the limit when n goes to infinity of this part? It's just going to be 1/3. Right? Leading terms. Okay. What's the limit when n goes to infinity of x? Remember, x has nothing to do with n. It's almost asking you, what is the limit n goes to infinity? 2. It's just going to be 2. What's the limit n goes to infinity? 3. That's just going to be 3 because you have no n inside. Then this is nothing but just 1/3 x. Okay? Good so far? Now go back and try to see why you cannot answer it. Because I need a number. I need to check if this one is less than 1 or bigger than 1. Remember? But if it's less than 1 or bigger than 1, it really depends on my x. So here's the logic. If I know x equals 1, I will know this one is less than 1, therefore convergent. Good so far? But if we do things reversely, if we want it to be convergent, we can just require L to be less than 1, and then we can actually solve for which x, which will actually make my L less than 1. So if you think about it, you can rewrite this one. You can take the 1/3 out, which is this. Now you can write down this. Okay. If the whole thing converge or diverge depends on how big this number is. It will be convergent if this is less than 1. It will be divergent if this is bigger than 1. It will be inconclusive if this is equal to 1. Okay. So basically what you're trying to say is, does it converge or diverge? Really depends on my x. But by writing this condition down, I can solve from x. Because this is not hard to solve. This is nothing but absolute value x less than 3. I times 3 on the other side. That means negative 3 less than x less than 3. Okay. This, if you solve it, is actually very easy to solve. It's just exactly the reverse. Bigger than 3. So you have x less than negative 3 or x is bigger than 3. So what did you just solve? Well, does it converge or diverge, the original power series? It depends on what kind of x you put in. If you put in 2.5, negative 2.5, 0, 1, negative 1, any number you put in which belongs to this interval, it will be convergent. If you put in negative 4, okay, or positive 4 or 5 or 6 or 1 million, it will be definitely divergent. Sounds good? So basically you know what will happen for whatever x you plug in once you solve everything up to this level. Moreover, these two will be exactly the reverse to each other. So actually if you know it is only convergent for this one, you almost already know it is divergent for everything which is not this. Okay? Then the third thing, we just need to verify for this case. We still have this case left because ratio test is inconclusive if you have equals 1. It may sound tricky at first, but if you think about it, really, you just need to check what happens when this equal to 1. In another word, what happens when this is 3? In another word, what happens if x equal to 3 or negative 3? Let's check it. Okay? Remember, your an, let's see, it is sum n from 0 to infinity, n over 3 to the n, x to the n. Now when x equal to 3, this one becomes sum n equal to 0, n over 3, n, 3 to the n. Oh, no, yes, okay, 3 to the n. They cancel each other. Am I doing the right thing? Okay, 3 to the n, and when x equal to 3, we have 3 to the n. So this is nothing but sum n from 0 to infinity n. Something is wrong? No, it's not wrong. Okay, clearly this is infinity, so divergent. Sounds good? Okay, what about x to the negative 3? Sum n from 0 to infinity. N over 3 to the n, negative 3 to the n, which is sum n from 0 to infinity, negative 1 to the n times n, which is clearly divergent because the limit is now 0 by test of divergence. So this is what we got. Convergent if x is here, divergent if x is not here, okay. And what if x is right on the edge? And you can see the equal sign goes here. Okay? And then what we can do is we can write down just this information. We don't have to write this down because we know anything not this will be this. Then we have something called the interval of convergence. In this case, it's negative 3 to 3, which is the interval. Sounds good? Okay, so this is how we do it. Basically, don't worry, okay? If you're a little bit lost, don't worry. Let's summarize the idea and then do several examples. Basically, what we do is we first do ratio test, okay? We try to see, okay, we try to make it less than 1 and bigger than 1 to get the part which is convergent or divergent. Then for equals 1, it's harder, but then we just check the ending points. Once we finish all these things, we write down our answer where the whole thing is going to be convergent. We call it the interval of convergence. That's basically the procedure. Okay, let's try several examples. First one. Okay. Sum n from 0 to infinity. X to the n, 3 to the n. Let's try that, and let's take a 4. Okay. Ratio test. an plus 1 equals xn plus 1, 4 to the n plus 1. So limit and what we have here is going to be limit n goes to infinity, xn plus 1, 4n plus 1, okay, times 4 to the n, x to the n, which is limit n goes to infinity. They cancel. You have a 4 left on the bottom. They cancel. You have only one x left on the top. You let n goes to infinity, and then you realize there's no n involved, so this just cancel. And then, when does this converge? It only happens when this is less than 1. Now let's go ahead and solve it. That basically means x is less than 4. That implies -4 to 4 for my x. That's going to be my interval of convergence, roughly. Okay? Now if you're here, which is outside this, you are definitely divergent. Now the only thing we are not for sure, because if this is bigger than 1, it's divergent. So that's easy. The only thing we're not sure is what happens if this one equals 1. We cannot simply say it's convergent or divergent. We need additional. So check the ending points. Okay. The ending points will be when x equals 4, x equal to -4, or x equal to 4. Now, when x equals -4, the original thing becomes sum n from 0 to infinity. Okay, -4 to the n, 4 to the n. What do you have? You have -1 to the n. Okay, the last few term will be -1 plus 1 minus 1 plus 1 minus 1 plus 1. By test of divergence, this is divergent. Okay, what about x equals 4? That's going to be sum n from 0 to infinity. 4 to the n, 4 to the n, which is sum n from 0 to infinity 1, which is 1 plus 1 plus 1 plus 1 plus 1 forever. That's clearly infinity. Okay, so either way, both of them are divergent. We can say finally, the interval of convergence, IOC, is going to be -4 to 4. Both are parentheses because we checked the ending points. They're not qualified. Okay. So ratio test first. You end up with a number. This number depends on x. Then to make it converge, you just say make it less than 1. To make it diverge, you just say make it bigger than 1, which is great. And every time you solve that, you end up with an answer. Now the only thing you don't have is what happens when something equals 1. But the great thing is, every time you have equal sign with the absolute value, you only have 2 things to check. So that's just some additional work to do to make the whole thing complete. Okay, let's check another example. This time, let's make things a little bit more interesting. Let's take x to the n. Let's take actually x minus 2 to the n over n times 5 to the n. Okay, if you write it down, it's going to be like, let's do n plus 1. It's going to be something like 1 over 1 plus like 5 over 2, x minus 2 plus x minus 2 to the square, 3, 5 square, which is 25. So keep going. Clearly, it's a power series. So again, ratio test. Okay, an plus 1 equal 5n plus 1, x minus 2n plus 1 over n plus 2. Limit n goes to infinity. An plus 1 over an is going to be limit n goes to infinity. 5n plus 1, x minus 2n plus 1, n plus 2 times n plus 1, flip f5 to the n, x minus 2 to the n. Okay, let's cancel. This one has one more 5. This one has one more x minus 2. Okay. Okay. 5 times x minus 2 times n plus 1 over n plus 2. Now, what's the limit of this part when n goes to infinity? Leading terms is going to be 1. The other two parts doesn't have anything. to do with n, so we'll just keep it. That's what we have. Now in order to finish, when will this one converge? When it's less than 1. That means you divide by 5. That means okay, that give you everything from 2 minus 1/5 all the way to 2 plus 1/5. This will be roughly your interval of convergence. Roughly. Why? Because if it's outside the interval of convergence, you will have bigger than 1, which is fine, it's divergent. But the only thing you're missing is when this thing happened to be equals 1. So check ending points. That happens when this equals 1/5. That means x equals 2 minus 1/5 or x equals 2 plus 1/5. Okay, you can go ahead and simplify. I chose to not simplify because you see the structure more clearly. Let's take a look. Okay, this here is the original thing. Let's plug it in. X equals 2 plus 1/5. Then the whole thing, I will copy it here. 5 to the n, x minus 2 to the n, divided by n plus 1. Okay, it's going to be sum n from 0 to infinity. 2 plus 1/5 minus this, that's going to be 5 to the n times 1/5 n plus 1. And you can see this one and this one cancel each other, which is nothing but this. Is this one convergent or divergent? Now go back to what we had before. You can use the integral test. Make sure this is decreasing positive and do the antiderivative of this. Or you can compare this one to be sum 1 over n, because technically they're basically the same. One doesn't really matter. To show that, you need to use p-series and you need to use the limit comparison theorem. But either way, I will save it to you, but this one is definitely divergent. Okay. What happens with this ending point? You have two of them, remember? Now you can see everything will be the same except for this one is going to be negative 1/5 n plus 1. Like I said, 5 to the n and 1/5 to the n, they cancel each other to give you 1. But because of this negative sign, you still have one more thing left. That will make this whole thing alternating. If it's alternating, we check, is this one decreasing? The answer is yes. Is this one, does the limit equal to 0? The answer is yes. So this one is convergent. Using the alternating series test. Okay, so here's what we have. We have an interval of convergence, roughly, and then we checked. For this one, it's still divergent, but for this one, it's convergent. So what we need to do is we need to add this side in to make it bracket to include this term. For this term, it's still divergent, so we don't have to do anything. So that will be my interval of convergence. Sounds good? That means if you plug in any number, as long as they belong to here, the whole series is going to be convergent. Otherwise, the whole power series will be divergent. Okay, we included less than one case in the ratio test, which is convergent, bigger than one case, which is divergent, and we checked the ending points. We chose to include this one, but not this one. Okay, so that's what we did for ratio test. So hopefully the idea is clear. You do the ratio test. Okay, you end up with something with x. to make it convergent, you'd ask it to be less than 1. Then solve and see what kind of x will satisfy that. You'll end up with an answer. This one will ignore the equal to 1 case. Therefore, that's why you need to check if the ending points are qualified. So some additional work. And when you have the ending points, you always have 2 cases. And after that, do you have convergent or divergent? Will determine, do you add them to bracket or keep it parentheses? And how to check it? You need to use everything you had before, from 11.3 all the way up to 11.7. Okay, let's try another example. I know it's kind of like a confusing object, but let's try another example. Let's put factorial in. This one becomes even more interesting. So, ratio test. n plus 1. Now, limit n goes to infinity. an plus 1 divided by an. That's going to be this. The first time you see factorial, it should be scary, right? It's not something we often deal with, but then if you are doing factorial with ratio tests, we say we kind of prefer that, because every time you do it, there is a guarantee you will cancel a lot of terms. If you don't understand this, go back to your notes. Okay, try to do several examples. If you have factorial, you increase 1 more, you only have 1 more. Okay, these two cancel each other, you have x. Okay, you end up with this one, and for tradition, we need to go ahead and solve when this one will be less than 1 or bigger than 1 or equals 1, right? After we take the limit. But now I want to ask you, what's the limit of the thing I just wrote down here? If it's kind of confusing, think about when x equal to 1. You're just looking at limit x n goes to infinity 1 over n plus 1. What's the limit? 0, right? What if x equal to 10? Then it's just 10 over n plus 1. What's the limit? 0. What if x equal to, I don't know, 1,000,000 plus a 3? That's just going to be 1,000,000 plus 3 divided by n plus 1 when n goes to infinity. It's going to be 0. Then do you realize this one is going to be 0 no matter what x you plug in? That means for all x, this one's 0. Is 0 less than 1 or bigger than 1? It's less than 1. So this one is convergent. And it seems like it doesn't matter what x we plug in, it's always convergent because the ratio test always gives you 0. Then what we can say is the interval of convergence is simply this. It's all possible numbers. Okay, that would be pretty interesting. Okay, so this case do happen. With this in mind, consider another case. That is this case. This is clearly a power series. We have 1 plus 1 factorial, 0 factorial times 1. Remember, this one is equal to 1, but that's not the focus here. Plus 2 factorial x squared plus 3 factorial x to the cube. Well, this is certainly something which is power series. Here are your coefficients. Okay, the coefficients are pretty big. Now, what would happen? Well, let's do a simple math. an plus 1 equals xn plus 1 times n plus 1 factorial. Ooh. Limit n goes to infinity. Let me make sure in case you get confused. Okay. an plus 1 divided by an is going to be limit n goes to infinity. Back to the n plus 1 times n plus 1 factorial divided by x to the n factorial. Again, let's cancel. You have x on the top. You have n plus 1 on the top. Okay, which is very similar to the case we had, except for this time n plus 1 is on the top, not on the bottom. Now try to ask yourself, what's the limit of the thing here? For example, if I put in 1, what's the limit? N goes to infinity. N plus 1. Infinity. Now what if x equal to 2? Infinity. Actually, whatever x you plug in, it doesn't really matter because you're just a constant. This part always goes to infinity. Alright, so the whole thing is infinity. Is it bigger or less than 1? Bigger than 1. This one tells you it's divergent. No matter what x you plug in. Think about it. Okay, whatever x you plug in, it doesn't matter. It's always infinity. It's always bigger than 1 if you run the ratio test. So it's always divergent regardless of what x you plug in. Okay, then your interval of convergence should be nothing. But now, what you really need to think about is, okay, maybe there is a special case. And can you realize for a very special value of x, this one can be not infinity? And it's not hard to realize since this part is super huge and this part is fixed. It's not going with your becoming bigger or smaller with your n. The only chance I can cancel that is when x equal to 0. So this one does converge, but only for 1 point. Interval of convergence is just 1 point. Or you can simply say x equal to 0. Okay, we have went over 5 examples. All of them requires a same procedure. Now if you go back to your notes, it's always start with a ratio test, finish, set it less than 1, solve an inequality which involves absolute value. Once you finish that, you check the ending points, you put them all together, you have your interval of convergence. I don't know why I put R there. Okay, that's probably because of my research interval of regions, intersection of regions, but that's different, not related at all. That's the procedure. But that also gives us another interesting observation. That is, no matter what kind of thing you do, think about what's going to happen. This is the first case. When you start to do the ratio test, right? Remember, you started with x to the n. That thing goes to x to the n plus 1. You take an plus 1 over an, you always have this term there. Together with some other terms, you try to solve an inequality which involves this, which is less than 1. Then there is a guarantee that your answer will always be an interval, like this. Okay? Think about what happens in the second case. You solve an inequality. Okay, again, this inequality is some number times x minus 2 less than 1. You do have the power, okay, and you do have a constant. Again, you solve an inequality which involves absolute value. Okay, and here's the answer you got. Cool. Now, can we just somehow sum and then you solve something like this? For number 4, where is it? Okay, you solve something like this. Again, it's a absolute value inequality you're trying to solve here. And finally, it's the absolute value of inequality you're trying to solve here. With that in mind, we can actually summarize if we do a ratio test for any power series, what can we expect? Okay. Let's think about a general thing. Cn x minus n to the n. Now you're trying to talk about an plus 1 divided by an. Limit. N goes to infinity. Okay? This is going to give you, take it back, limit n goes to infinity. Cn plus 1, x minus a n plus 1, divided by Cn, x minus a to the n. These two always cancel. So you will have limit n goes to infinity, an plus 1, a cn plus 1, which is just the ratio between the coefficient divided by cn, okay, times absolute value of x minus a. Then you set this one to be less than 1. Okay, this will be always the case you have. Then what can happen? Well, several things. First case, this part is infinity or divergent. Then basically nothing converge except for x equal to a, which means you have a 0 here. Okay, as long as this part becomes infinity, nothing will happen. Okay, for this you can see the example 5. I don't want to switch back and forth. So this will be the case. Now that happens when this happens. Second, cn plus 1 over cn limit n goes to infinity is 0. For this, you can see example 4. If that happens, this part becomes 0. Then whatever x you plug in, it will converge. So this one converge for negative infinity to infinity for anything. Good so far? Okay. Third possibilities. So we try to look at this thing, right? This thing at the front. If this is infinity, whatever x you plug in, it doesn't matter. It always diverge. So the only thing convergent will be you have 0. That is x equal to a. If this part is 0, then it doesn't matter what you plug in. It's always going to be convergent. Then for every number, negative infinity to infinity will be the answer. Number 3, this one is going to be a number. Let's say this one equals 3. Then what you're going to have is 3 times x minus a. That's that one. What you're going to do is you're trying to solve this one. So it's going to be x minus a less than 1/3. And the way to solve this one is always give a negative less than this and give a positive. Then your final answer is going to be a minus 1/3 less or x less than a plus 1/3. Okay. Now, of course, if you have something other than 3, you could just take this to be L. Then this one is going to be L. This one is going to be 1 over L. This is going to be 1 over L. And so on. Okay. Good so far? Now, what is this, if you think about it? Let's draw it. It tells you this is A. Okay. This is 1 over L, whatever that number is. Can be bigger or less than 1. So this is A plus 1 over L. And this is A minus 1 over L. And your x will be convergent. Your power series will be convergent if x belongs to here. So this is the interval of convergence. Now, if you take a look, what does this one look like? Do you realize it's always equal distance from the left or to the right of this A? Because you have an absolute value. Absolute value means go negative and then go positive, okay, from this thing here. So no doubt, A is called the center. And this interval, because it's exactly symmetric, we can define the radius of convergence, of the interval of convergence. In this case, it's nothing but 1 over L. Okay, so that will be the radius of convergence of your interval, which tells you how big, okay, this interval is. This A tells you where the center is. This 1 over L tells you how you can shrink or stretch the interval. Okay, sounds good? Okay, so with this in mind, we did ratio test for all the examples we did. In general, it all narrowed down to a simple inequality which looks like this. And then what kind of answer you get really depends on what the limit of the coefficients are. Okay, and we have 3 possibilities. This part can be 0. Then it's always convergent. Whatever you plug in, it's 0 less than 1. This part is infinity or divergent. Then it's always divergent, whatever x you plug in. Okay, therefore, you're only convergent when this part is 0, which means only convergent for 1 point, that is x equal to a. You're basically adding a lot of 0 together. Okay. Number 3, maybe this one is a constant. Maybe it's 3, maybe it's 5, maybe it's 1/2, whatever. But then you will be ending up solving an inequality looking like this. It has absolute value. Okay, then whenever you solve this one, your answer will always look like an interval. But this interval is very special. This interval is going to have a center. The center is exactly A. Okay. This interval will go equal distance to both sides because of the absolute value. And the equal distance you go from both sides will be the radius of this interval. We call it the radius of the interval of the convergence. Or in short, the radius of convergence. Okay. To summarize the result, let's go back to the theories. Okay. That's exactly what I just said. For this one to converge, you only have 3 possibilities. Number 1, only a single number. Number 2, all possible number. Number 3, an interval. This interval is very special because it has a center, which is A, and it goes to the left by R to give you A minus R, and it goes to the right by R to give you A plus R. This R basically is called the radius of convergence. This one tells you how big or how small the interval is. This A only tells you the center by shifting to the left or the right. Okay, so let's go back to the example. For the first example, for the second example we have here, take a look. What's the interval of convergence? It's -4 to the 4. That's what we got here. Now, if you clearly look at it, it's actually 0 minus 4 to 0 plus 4. 0 is the center. Why? Because we have x to the n, which is x to minus 0 to the n for the general form. So the center is 0. Radius of convergence equals 4. So the total length is 8. You go 4 to the left, you go 4 to the right. Yeah. Now look at number 3. Our final answer is going to be here. And that's the reason I wanted to keep thinking this way. Do you see the center? The center is going to be 2. The radius is going to be 1/5. Okay, because you start from 2, you go to the left by 1/5, you go to the right by the 1/5. Another thing you should realize is this R tells you how big the radius is, basically tells you how big the interval is. But this R doesn't tell you anything about ending points. Okay, even though you say I'm centered at 3, I go 2 to the left and 2 to the right. It gave me from 1 to 5. But you will never know should you put bracket or should you put parentheses here. So for our case, R only tells you how wide the interval is, but for ending points, R don't give you that information. Therefore, just knowing the center and the radius of convergence give you most of the information, but it doesn't give you all the information because you're missing the ending points. Okay. Like we said, now if you think about it, we clearly have a case where the coefficient give you 0. It doesn't matter what x you plug in. So you have it's always convergent for any x. This basically tells you the radius of convergence is infinity. This one tells you the radius of convergence is 0 because you're just a single point. Okay. What does it say? It simply says if you have a function like the one we just wrote, if I remember correctly, it's going to be something like this. Okay. We're trying to replace this one locally by a power series. And then there is a guarantee that this one will not work for general cases, but only for very, very restricted x. You can solve it. You will have an interval. On this interval, this one works. And you will always have a center. You will always have this equal distance from the center to tell you, okay, it only works for an interval look like this, with a center, and go left and go right by an equal distance, which is the radius of the convergence. So that is how we verify the convergence of a power series. It will, if you are really lucky, the original function is really great, then you may have a polynomial to represent this function for all the possible numbers. That basically means the whole thing is just a polynomial. Okay, but in general, what you will have is actually this whole thing is just locally a polynomial because it only works for an interval outside the interval, the power series won't work. Okay, which kind of makes sense. Otherwise, we basically get free lunch, right? It's like every function can be represented by a power series, and power series are really easy, and there's no restriction. Then it seems like free lunch, right? So we should have some restrictions. That is, yeah, you can do it, but under some restrictions, you can only do it for a certain kind of number. You cannot do it for all possible numbers. Okay, so that's what we have. Now, finally, I want to revisit what we had from the examples and let you take a closer look for all the radius of convergence. I'm just going to write it down. For this one, the radius of convergence. Oh no, let's do the first one. You can check it. I just copied it from the examples we did. For this one, the radius of convergence is 1. Okay, remember it's absolute value of x less than 1. The center is 0. Okay, the radius is 1. Okay. For this one, r equals 4 because our answer is negative 4 to the 4, if you remember. For this one, let me make sure I'm doing the right thing. R equals 1/5. This is 2 minus 1/5 to 2 plus 1/5. For this one, R is infinity. Finally, for this one, R is 0. It only works for 0. Okay, let's talk about this. For this case, I think it's very easy to understand because of geometric series. You take a geometric series, you take the sum. It depends on how big is your R. Your R has to be less than 1. Okay, so that's our benchmark. Good so far? Okay, now think about this. What happens with this? This is still geometric series. Can you see that? The only difference is x over 4 is now your new ratio. Okay, then before you require the ratio to be less than 1, you still require the ratio to be 1, less than 1. But in order for this one to be less than 1, if you take the absolute value, your x can be a little bit more relaxed because you have a 4 on the bottom to help you to converge a little bit. In other words, if you put a 4 to the n on the bottom, what's going to happen? It's going to make the whole thing smaller. It's going to make it easier to converge. That means your x can behave a little bit naughtier than what you did before, which is between negative 1 and 1. Now you can actually stretch to negative 4 and 4. You're still okay because your big brother is still helping you under the bottom. Okay. So basically this one is the power series. And if so far you should have realized power series is nothing but the geometric because power series is x minus a to the n. That's exactly a geometric, right? So if you divide a geometric by another geometric, what's going to happen is it's going to change the radius of the interval, radius of the convergence. Okay, in this case, it make it bigger because you're helping. Make sense so far? Okay. Now think about what's going on with this. Number one, you have an n plus 1 on the bottom. Okay. Now, I think we went over this one in the limit comparison test or ratio test, I don't quite remember, but if you have a power series and you have a polynomial here, polynomial does nothing to the convergence or divergence, but only to the ending points. Okay. With that in mind, we can basically ignore the thing on the bottom. Now what happened? You still have a interval of convergence, right? You still have a geometric series, but this time what you have is, for me, I need to make sure my radius is 1, but now you give me another 5 to the n to make me bigger. Okay, make it harder for me to converge. Then, for me to converge, I need to do extra effort to cancel the negative effect brought out by this 5 to the n. So if this one increases the whole thing by a scale of 5, my radius of convergence should reduce by a scale of 5 so that I can still be in this 1 range. That is why if you put a 5 to the n on the top, you're not helping, you're making things worse. Okay, Therefore, I should scale my corresponding ratio to be 1/5 of the original scale. Good so far? Great. Okay, that's actually very, very interesting. So basically, if you have x to the n, okay, and you give it another thing, okay, times another term, which is like 1/3 to the n. If before the radius of convergence is 1, now the radius of convergence can be 3 now. Why? Because this one is helping. It's making everything smaller. But if you times it with 3 to the n, what's going to happen? Now instead of saying, hey, you need to be less than 1, the whole thing should be less than 1. That means your radius of convergence should be changed to 1/3 because this one came here to screw things up. It's not helping because it's not on the bottom. You make the whole thing bigger. Therefore, this one needs to actually be smaller than before. If you become bigger, this one has to be smaller than before. That's why putting this one on the top is actually going to make your radius of convergence smaller by a factor of 3. Okay, so that's what happens if you have a geometric combined with a geometric. If you have a geometric combined with a polynomial, basically, if the original radius of convergence is 1, this radius of convergence is still 1 because you compare to a geometric which is exponential is nothing. Polynomial is nothing compared to a geometric. The only trick you can do for this part is maybe you will change the ending point a little bit. But for the bigger scale, you won't change a thing. But now, what happens if you put a factorial with a geometric? We all know factorial is way bigger than geometric. Okay, that means if I put a factorial here, which dominates my geometric, which means whatever your geometric does, my factorial doesn't care. Okay, because I'm so big compared to you. So if I'm helping, you will have the best help you could ever had. That is, you will always converge. Okay, that gives you an infinity. But if I'm not helping, I'm making you bigger, which means I'm making things worse. No matter how small you make yourself be, it will never be able to cancel the negative effect I have. So whatever, you will never converge anymore, except you go to the extreme and make yourself 0. Okay, so if you're thinking about the radius of convergence, it's really, you start with something very simple, the power series, okay, which give you r equals 1. And then you start to add the coefficients to change this r. You add a polynomial. Compared to geometric, it doesn't change r because they're so small. Now if you add a geometric, another geometric, it depends on if you're helping or if you're making this worse. For example, if you're helping, then it's easier for me to converge. My radius can now be 3 now because this 1/3 is helping me. But if you put it on 3 to the n, well, you're actually making my life harder. But I can still accommodate to make the whole thing less than 1. I just take myself to be less than 1/3, then together we can still make the whole thing converge. But if you put factorial, basically this x to the n part, just say I gave up. Okay, it's your game, factorial. If you want to help, it doesn't matter what I do. If you don't want to help, it still doesn't matter what I do. So if you want to come here and help, which means you make my whole thing smaller, then I have the best help ever. I have infinity. But if you come here and say, hey, I want to screw everything up, then there's nothing I can do. I just say, hey, there's only one case I can converge. So that's what's going on with the radius of convergence. It really depends on what kind of a coefficient you have. If the coefficient is a polynomial, just change the ending points. If the coefficient is another geometric, you stretch it, you shrink it with the corresponding ratio. Okay? If you're helping, make it bigger. If you're not helping, you make the radius of convergence smaller. But if you add factorial, basically we just throw the white tower and say, hey, we give up. Okay, that's all we need to know about power series. Let's recap what we have really quickly. You have a function. You want to rewrite it to be a power series. Then everything will become easier, but there's no free lunch. You need to know the interval of convergence because this one only works for a certain type of x. Now we introduced the definition of this. We also introduced, if you know a power series, how do you find the interval of convergence? Basically, you use the ratio test. at any point. Next section, we will talk about given a random function. Actually, not a random function, give you some function. How do you write it to be a power series? Okay, it's kind of confusing the first time you see it. Try to see the big picture and also try to do several examples. You need more examples. The procedures are really standard. I won't say easy. It's really standard because it's always blindly ratio test. And your answer will always look the same. It's always a center with a radius of convergence going to the left and the right for the same distance. So do enough examples, you will start to see this pattern. Hopefully, if we do this for long enough time, you will start to see the big picture behind it. But just want to warn you a little bit. Every time I teach it, people always struggle with this in the exam because they are still not familiar with the procedure. Okay, so try to do a lot of examples and bring the questions to the office hour.